Hi. Now we're going to compute how far it is to go along a path that is given as a set of points, including looping around and back to the first point from the last one. So it's a going around in a loop. It doesn't actually matter where we start. It doesn't matter the direction either. It's just the total distance. Let's start off by having some points defined that we can work on. We know from the problem description that this is supposed to give 12 as a result, so we have a little bit of a sanity check here. Okay, we can start by making a lambda that we're going to apply to the points, and the right argument on the right side is referred to as omega. And we're going to go through and follow very closely how the problem is described. So we want to connect the last element with the first element. So we can get the first element with the first function extracted, but we need it to be enclosed to be fitting into our format of enclosures here, vectors of vectors. And then we want to append that to our original input. Okay, so now we got the same point over here as we have over here. This means we can just consider adjacent elements. So we've got these two adjacent elements, we want to measure the distance from between them, and then these two elements, and we want to measure the distance between these two elements, and then we add it all together, and that's going to be our result. So adjacent differences, that is a windowed reduction. So this is a subtraction because there's a difference, and reduction, but not on the whole thing, just over windows of size 2. So this should give us 3 results. Okay, now we need to use a little bit of trigonometry. You may know that if we have a right-angled triangle, then the diagonal, so to say, is the square root of the sum of the squares of the sides of the triangle. So if we look at this as a triangle, we moved 3 steps in one dimension and 4 steps in the other dimension, and those dimensions are orthogonal to each other. That means the total distance traveled is the sum of the square root of the sum of the squares. So it's going to be 16 and 9, that's 25. The square root of that is 5, and so on. So for each one of these pairs, we'll make a new lambda, and we call it on each one. That's the each operator, which is like a map. We want to take the first element, so that's the same first function here, and we want to take the last element. Last element is the first element on the reversed argument. So this is the first and the last. This is not going to make any difference at all so far. But now we can do the math on them individually. So we're going to take the square of this one. So this is the exponentiation function, but it takes the exponent on the right. So we use the commute operator to put it on the left, and we want to do that over here as well. And then we can add them together like this. So now we get 25 here and 16. That's 0 squared is 0, 4 squared is 16, square root, and so on. And now that we have these, then we can take the square root of that whole thing. So square root is the same as raising to the power of a half. And finally, we can sum up everything with a plus reduction. This is all very well, but I think we can do a little bit better. Let's give this one a name, this function a name for later, so we can do some speed comparisons. And now we go up and edit this. So our first observation here is going to be that we are picking apart an argument that has exactly two elements. We could also insert this function between the two elements. So since there are only two elements, then this is the same thing as a reduction. So if we reduce on a two-element vector, that's the same thing as inserting that function between those two elements. This means that what we have on the right, the last element, is the right argument, and the left element is the first one. So alpha refers to the left argument. Fine. But we can further observe that all we're doing here are some scalar operations. We're doing a square of both, and then we are adding them together, and then we are doing the square root of it. So before we get to that square root, we could just take the entire argument, the entire pair, so go back to removing this reduction, the entire pair as a two-element vector, and using APL's array capabilities to do the squaring on this list of two elements. And then we can combine everything afterwards. So let's illustrate this for a moment. We'll just remove this here and remove the summation. Okay, so now we can see that we squared each pair. Here. Okay, so that means we can now do the summation of them. And then we can do the square root. And we're ready to sum again. Right? What else can we do? Next, what I would do here is move this square root over on the left, avoiding the parentheses. And we can do that by commuting with the exponentiation function again. So we are using commute operator for that. And the reason I like to do this is not just to save the parentheses, but also to show a certain symmetry. We've got the commuted power here, and we've got the commuted power here, and they have inverse left arguments. So we can see it's this transformation and then undoing that transformation. And I'd actually like to take this even further. Let's try running this first. I want to show the symmetry of this 2 over here. And we can do that by, remember that this 0.5 actually goes over on the right because of the commute operator. So we can pre-process the right argument to the power function with the reciprocal. So we have a pre-process combinator operator, and then we have a reciprocal function. So this is the division symbol, but when we call it with one argument to pre-process things, then it's going to be 1 divided by, or the reciprocal, which means we can state this as a 2. And now we can see a very nice symmetry here in our code. Okay. Next observation is that this is a scalar operation. Scalar operations also penetrate into all structure, but we have an outer explicit loop here. We don't need to have this scalar operation done piecemeal on each pair. We can do that outside before we even go into a looping mode. Then we sum each and post-process again with a scalar operation, which is the square root. That doesn't need to be inside the loop either. So let's take that out and have the looping just be the summation. And now the only thing we have in our looping lambda is a wrapped derived function, the plus reduction, the summation. So there's no reason to wrap it in a lambda in itself. We can just apply it directly. This side over here, I want to have a look at as well, because what is a pairwise difference? It is just comparing, in this case, subtracting every element with its neighbor. So if we take all the elements and we shift them around one step, rotate them cyclically, then we get the neighbor element. And then the first element becomes the last element and gets paired up there as well. So instead of explicitly adding another element and then doing a pairwise difference, we can just do a subtraction which goes on the entire array with the one-step rotation of the right argument. So this is the rotation function. One step, we take the first element and put at the end. So now the elements here are the neighbor elements of the ones over here. Right. Let's call this G. And we'll get to a speed comparison between these two in a moment, because I want to go one step further. Notice these points that we have. The reason we need to loop over them is because they are enclosed. We have vectors of vectors, but APL excels at operations on entire arrays. We can make this into a simple single array using the mix function. So every vector here becomes a row in a matrix. And now, if we were to find the neighbors, it would be the next row over. So we can rotate. This time we're rotating vertically to get the neighbors. And from here on, everything would be the same. So we can take the mixed points and subtract them from our points. And then we want very much the same formula as up here. We're going to do the squaring. And now we need to sum the rows. So no need to do any explicit looping here. We just sum, and this goes along the rows. And so on. The rest of it is the same. And this gives us the same result. The only difference here is that we started off by mixing, so we get a single flat array, and then we do the rest of it, of our computation on that flat array. So we can give this a name, and this is a top, a two-train, two functions adjacent to each other. There's our main computation function, and then there's a preprocessing function which just starts by mixing all these points into a single matrix of points, with one point in each row. Okay, now for performance comparisons. For that, let's generate some test data. We can take 10 rows and 2 columns, reshape as 0, and throw in the random roll function on that. That gives us a bunch of numbers between 0 and 1, which is fine. These are floating point numbers, good for our purposes here. It doesn't actually matter what the values are, because whenever you're subtracting and squaring so on, it's just the same operation. Now, the specification is that we're getting a vector of vectors, so we split. So before we were using mix to join together vectors of vectors into a matrix. Now we're going to use the opposite down arrow to split the matrix into a vector of vectors. And let's give this the name Q for our quality assurance. But we should also not use just 10 points. Let's use 1,000 points. Right, now we're copying in the compare execution tool. We copy that from the defense workspace, it's a library. And then we give it expressions to compare. So we have F on the points, and G on the points, and H on the points. And let that run for a little bit. to see how they stack up against each other. And well, that's pretty impressive, isn't it? So just doing some cleanup work, not really changing anything in how we're computing, that got rid of a good 20% of no, almost 80%, leaving only 20% left of the computation time and therefore resources. But switching to doing things in an entire array manner by starting off with some flat data, not nested data, that pretty much eliminated all the work that we needed to do. So bear that in mind. Want to go fast? Stay flat. Thank you for watching.